question is, how do we solve an extensive form game? I mean, what is a appropriate solution concept for extensive form game? The simplest, the most straightforward definition or equilibrium notion is Nash equilibrium. So let's apply the Nash equilibrium in an extensive form game. Well, how do we define it? Well, simple. A Nash equilibrium in mixed strategies of an extensive form game with set of players, histories, player functions, if nature moves, this is its distribution, information sets, and the payoff function for each player, well, is a mixed strategy profile sigma star, all right, which is a strategy profile such that for every player, I in N, nature is not a player, playing according to the prescribed strategy sigma I star is at least as good as playing any other pure strategies player I might have, given that conditional on his or her opponents are playing according to this strategy profile. And that's true, as I said, for every SI. So put differently, sigma I star must be a best response to sigma minus I star. All right, or put differently, sigma star is a Nash equilibrium if no player has incentive to deviate, or sigma star is a Nash equilibrium if no player has a profitable deviation to a pure strategy. All right. Well, don't forget, we did similar arguments before. We may say this payoff is greater than or equal to this payoff, meaning player I has no profitable deviation to any mixed strategy, but because the utility function is linear over the set of probabilities for player I, you don't really have to worry about mixed deviations. Just look at the pure deviations. Well, don't forget, this is an extensive form game and strategies are complicated animals. It's not like the prisoner's dilemma, cooperate defect, like two actions and so hence two strategies. So strategies are more complicated. All right? Well, remember, whether this game is an extensive form game or not, we can always write what's called strategic form representation or normal form representation of an extensive form game. How so? Well, simple. Use exactly the same players. Well, once all these histories and players and actions are given, we are going to create pure strategies for each player, right? I mean, in order to talk about mixed strategies in an extensive form game, you first have to create the pure strategies and then use the same payoff function. So from this game, I can reduce it down to something much more simple. Just the set of players, just their strategies and their payoffs. So this is going to be what's called a normal form representation. So a mixed strategy equilibrium, mixed strategy Nash equilibrium of an extensive form game is in fact a mixed strategy Nash equilibrium of its normal form version. All right, once again, a mixed strategy Nash equilibrium of an extensive form game is identical to Nash equilibrium, mixed strategy Nash equilibrium of its normal form representation game. All right, and don't forget, because every finite normal form game has a Nash equilibrium, well, then that means every finite extensive form game must have a Nash equilibrium. Maybe in pure strategies, maybe in mixed strategies, but that's the general, the most general format we can provide, because remember, every pure strategy is also mixed strategy, but not all mixed strategies are pure strategy. Well, what if I want to use behavioral strategy? Well, fine, you can do that. I can then slightly change the definition. How? A Nash equilibrium in behavioral strategies of an extensive form game is a behavioral strategy profile. Behavioral strategy profile. Well, we don't use the notation sigma, but we call the notation beta star, which is in this fat B set, such that for every player I in N, well, again, we just change the notation, beta I star, comma, beta minus I star. So this is the behavioral strategy of player I. This is the behavioral strategy of all the other players. Greater than or equal to payoff of the player, as again, this is an expected payoff. Given that the others are playing exactly the same strategy for every SI in SI. All right, so that's it. Once again, this is how we define the behavioral, Nash equilibrium in behavioral strategies. Well, the thing is the behavioral Nash equilibrium, the Nash equilibrium in behavioral strategies, is it equivalent to mixed strategy Nash equilibrium? Well, yes, exactly. Why? Well, because as I said, for every mixed strategy, there's outcome equivalent behavioral strategy. And for every behavioral strategy, there's outcome equivalent mixed strategy. So if I have a Nash equilibrium in behavioral strategy, I can transform those strategies into mixed strategy and then come up with an outcome equivalent Nash equilibrium with outcome equivalent mixed strategies, or vice versa. All right. So whether you use behavioral strategy or mixed strategy, the Nash equilibrium, the Nash equilibrium strategies will obviously be different because you describe strategies differently, but outcome-wise, they're going to be identical. Okay? And again, every game has a Nash equilibrium, whether you calculate it with mixed strategies or behavioral strategies.